Hello everyone, welcome back. Today we have Rob will tell us about the Vafa-Witten bundles over P2 with examples.
Yeah, the titles, Vafa-Witten bundles over P2 with examples. I'm actually not going to talk about Vafa-Witten bundles today because there's such a big historical background with these things um, that, Vafa-Witten bundles in a way are generalization of Higgs bundles. They are Higgs bundles. And so I thought it'd be appropriate to just talk about Higgs bundles today, give a historical background of Higgs bundles. So today's talk is just going to be Higgs bundles, what they are historically, some results, and then at the end, I'll probably introduce Vafa-Witten bundles, and then that'll be it. And then I'll do like a part 2 or something like that. Okay, Higgs bundles. First, the setup is I'm just going to be working over a complex curve, so just a Riemann surface. So today, everything's going to be done on a Riemann surface. So let X be a compact Riemann surface. So this is just a complex one-dimensional compact manifold. So a one-dimensional compact complex manifold. And I'm going to assume that the genus is going to be greater than or equal to 2. So I'm going to assume that the genus of my Riemann surface is greater than or equal to 2. I'm excluding genus 0 and genus equal to 1. Yes. Yeah. I'm excluding. Yeah. So when G is 0, you're at P1, and genus is equal to 1, you're at an elliptic curve, and then genus greater than or equal to 2, you look like something like, I'm so bad at drawing these donuts, but what am I doing here? I want to draw this. How do people do this again? Like this. Okay.
Like a smiley face with a tiny frowny face.
Yeah, that's what I want to. Yeah. I want to do like it's gonna look like this, and it has. Yeah. There you go. Yeah, these are the amount of holes. So I'm assuming there's at least 2 holes in this surface. So this is going to be X. I'm going to construct I'm going to I'm going to call this mathcal E. It's going to be a pair. It's a holomorphic vector bundle. So E, a holomorphic vector bundle of rank R and degree D on X. So when I mean this pair, I mean E is itself a rank R complex vector bundle on X, and partial bar E is an operator that defines a complex structure. So partial bar E, so this is a map from sections of E. So it takes in a section of E and sends it to sections of E, tensor the 0, 1 part of the cotangent bundle of X. So it takes sections of E, sends it to the section of E tensored by, dz bar. So this is a Dolbeau, capital D, Dolbeau operator on E. And how do we define sections of curly E? We have that the sections of curly E are just going to be the set of all sections of E such that partial bar E of S is 0. So I'm just going to be thinking of this as a sheaf of sections, sheaf of holomorphic sections with respect to this Dolbeau operator E.
Tell me why this defines a complex structure. Why such a defines a complex structure.
It defines a complex structure in the sense of, now you're testing my memory here. It defines a complex structure because it squares to 0. Right. So yeah, it's not a complex structure in the sense of like of an I squaring to one. It's a complex structure in the sense that its curvature vanishes, and this defines. You can prove that the total space of this thing defines a complex manifold. All we really need from this is that um, this curly E is a complex vector bundle with some operator, and I call this thing holomorphic because its sections are going to be holomorphic sections of this complex bundle here. So holomorphic in the sense that d bar S vanishes. Yeah. So this, yeah, we call this thing a complex structure, but you can call it a double operator on E. It defines what does it mean for a section to be holomorphic. It defines holomorphicity of yeah. So do I want to go into, let's see. So what we can do in a specific setup here, I'm going to assume that this Dolbeau operator comes from some Hermitian metric on E. So suppose E has a Hermitian metric H, and that, so it's a Hermitian metric H with associated Chern connection. So H defines a Chern connection, or it defines a connection in a canonical way, similar to how the a Riemannian metric defines a Levi-Civita, a metric connection. So it's defined in an analogous way. In fact, it's actually going to be defined by the equation H inverse partial H. And I'm going to assume that this is a Chern connection such that in the decomposition, so because X is a Riemann surface, is a complex manifold, it has a complex structure, so the tangent bundle decomposes. So, well, specifically the cotangent bundle decomposes into its 1,0 part and its 0,1 part. This is because since X is complex. So we get this decomposition for free, and I'm going to assume that this thing decomposes, well, it does decompose into two operators, which I call partial RE, or partial E plus partial bar E, with partial E is a map from sections of E to sections of E tensor the 1,0 part, and partial bar E is exactly the this thing that I call the Dolbeau operator. E O times T star 0, 1 X. So because X is complex, we get a free decomposition of the cotangent bundle. And as a result, this connection, which is a map from sections of E into sections of E tensor T star X, the cotangent bundle, because of this decomposition, we get a decomposition of this operator. Yeah.
I have two questions.
Yeah. Yeah.
So the first one, what is the partial that we're applying to our function?
Yeah. So how do I want to describe this? This really is just going to be, so if I write H, so this here, if I write H in coordinates as Hij, then when I write partial H, I really just mean like the exterior derivative. So it's going to be partial Hij d z I. Yeah, exactly. Yeah. That's kind of what I mean. Yeah. So this is not quite. Yeah. So this put a, okay. I'm misremembering right now, but put a this is like an asterisk here. This is not quite correct, but this is in essence what we're doing. This is just really what this looks like in coordinates locally. So this is a local equation. It's not a global equation. Yeah, it's similar to that. But it's just that, yeah, in coordinates locally, what does this thing act as? It acts like this. This sometimes people write as d of log h, right? Because this is almost like a logarithmic thing, right? Yeah, you know what I mean? Yeah, yeah. So there's a way that you can describe log of h kind of globally, and d of log h is that's kind of the global, you know. Yeah.
The other thing I want to maybe it's not important, but
Yeah.
is this decomposition, is that orthogonal with respect to the metric? Like once you extend the metric to the exterior bundle?
Like, does this become orthogonal with respect to the metric, or
the decomposition of your cotangent.
right here? Yeah.
Is that orthogonal? Do we care if that's orthogonal with respect to h?
Like, I mean, like if I take h and I apply it to something here, and if something here I get 0. Canonically, don't quote me on this. I don't think so, but I think you can complete it to some basis in which that is true, because that's like because I think because this is what sometimes people call like a unitary connection, and so by unitary you have like it's unitary in the sense that so this thing here satisfies it's compatible with the metric in the sense that if I have g u nabla hv plus g nabla huv, I get 0. I think is that the condition. But yeah, again, that's a good question. Orthogonality, you can construct an orthogonal basis or a frame such that you have that, you know, it's an orthogonal splitting, but I'm not sure if it's canonical. I can't. Yeah.
The question that I had is that for the connection, the term connection, like in gauge theory, we usually have like G inverse del G plus I think G inverse A G, where A is some like algebra one form. Do we have something analogous here, or is it always gonna just be that one term? No.
No, you will in general have some that Lie algebra valued kind of thing that you're talking about. That A, we have something here, but it's just gonna be a matrix of one forms. Yeah. So you can write it as D plus A locally, where A is gonna be well, yeah, it's going to be some matrix of one forms, but then within that matrix, because of this decomposition, I have these two operators. Typically, people focus on this one because this is what defines holomorphicity for this bundle here. And this thing decomposes locally as, so partial bar E acts on sections. So this acts on sections of E. And if I have some local frame, so if like say SI is a local frame for E, then how does this thing act? Partial bar E is going to take an SI, and it's going to be how do I want to write this actually? How do I want to write this actually? Hang on a second here. So, okay, local frame then, so it's actually going to act like if I take SI and I multiply it by some function, it's going to be partial bar of F tensored with SI plus, I mean, this is just the what is that called? Leibniz rule, thank you. F of partial bar E, yeah, nabla E, SI. So on locally on functions, it's really just going to be partial bar, and then this thing we can write as this as like AI Sij or something. Or sorry, other way around. IJSJ, where this Aij is kind of like your I that you were the A that you were saying. And this is just going to be a matrix of one forms. Yeah, yeah. So, where am I now? Yeah. Okay. So I have this. So when I have a Hermitian metric, I essentially get a decomposition of the Chern connection for free using the complex structure of X. And this operator here, I can use it to define holomorphicity for E. So I'm using this d bar operator here. So d bar E makes E holomorphic, which we write usually as curly E. And it's going to be a tuple to keep in mind that the base bundle is a complex bundle. And I have this operator too here, d bar E. So I can think about the curvature of this thing. So the curvature of nabla H is, so it's going to be FH, and it's just going to be this thing squared, right? So just like the Levi-Civita connection, you square it, you get your Riemannian curvature. Here, I'm going to write the curvature as F sub H, and F. So, okay, well, what is this exactly? In this decomposition, I can write F sub H as partial E plus partial bar E squared. And if you actually write this out, okay, so you get a lot of stuff. You get partial E squared plus partial bar E squared plus partial bar E, and then plus partial E, partial bar E. Now, we're on a Riemann surface, which is complex dimension 1. So what is this thing going to be? This thing here is going to be a 2, 0. So it's going to be a 2, 0 form. This thing here is 0, 2. And then these are both 1, 1. But because we're on a Riemann surface, dimension 1, there are no 2, 0, there are no 0, 2 forms. So these are 0 trivially. So this just gives you partial bar E plus partial E, partial bar E. Since there are no 2, 0 forms, 2, 0 or 0, 2 forms on X because of dimension reasons. It's dimension 1. So the most you have is only 1, 1, right? So you only have like dz wedge dz bar. There's no dz wedge dz, that's 0, and there's no or dz bar wedge dz bar, that's 0, and there's no dz wedge dz, that's 0. So, in other words here, so FH lives in, so is a section of the bundle, and I'm going to write this as omega 1, 1, 1, comma 1, and E. So it's an endomorphism of your bundle. So you can think about it locally. It's just a matrix. It's an R by R matrix, and the entries are 1, 1 forms. So locally, FH is a matrix with entries. They look like Fij dzi wedge dz bar j. Right? So this is a 1, 1 form. dz wedge dz bar. Okay.
And the reason why it's a matrix and is running isomorphic to GL R. Not necessarily GL.
Yeah.
And it's all bundle.
Yeah, end is all endomorphism. So you're right. Locally, on each fiber, these are just endomorphisms from the fibers of E to the fibers of E. So those things will be like GLC, GLRC. What if they're not invertible? So these they don't have to be invertible, right?
So it's more like N by N.
Yeah, 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 yeah. Yeah, exactly. Yeah. The GLN ones, those will come up. Those are going to be, we call them the automorphisms of E, which are the invertible endomorphisms.
Whereas in this case,
Yeah, so NE as a bundle is isomorphic to E tensor E dual. Yeah. Yeah, exactly. So, okay, what do I want to do now? Now we have the pieces. I want to define what I mean by degree of this bundle. So I have that this thing is rank R, and then I said degree D. What is degree? So rank is simple enough. It just means that on each fiber, it's an R-dimensional complex vector space. Degree D, what does this mean? So the degree of E of the holomorphic vector bundle E is, so we write it as degree of D, and this is going to be, well, it's really just the integral over X of the first Chern class of E. Curly E. But this is also the first Chern class. What is this? This is going to be I over 2 pi times the integral over all X of the trace of F sub H. When I mean trace, I really do just mean, so locally, what is this going to be? Well, it's a matrix of 1, 1 forms, and I'm just going to take the trace. The trace, so this thing here locally, I'm just going to be integrating 1, 1 forms, which is fine because that is, if I write it in its real parts, it's going to be a 2 form, and this thing is a 2-dimensional real object, so this is fine. So this makes sense. So this is how I'm going to describe or define the degree, and yeah, this is what I called D. D to be the degree of E. Yes, okay, perfect. Now I'm going to go to a classical theorem of Donaldson from 82. I guess I'll go over here. Although I do have to define some things first.
Ask one more question.
Yeah.
So it's kind of a motivational question. So
Yeah.
given a complex vector bundle over a Riemann surface,
Yeah.
why do we need an operator to determine what a holomorphic section should look like? Because in the smooth case,
Yeah, in the smooth case, so when I mean that this thing is a holomorphic vector bundle, well, you need to define what do you mean by holomorphicity, right? So E as a complex bundle has a sheaf of sections. It has sections, right? These sections are smooth, right? I can differentiate them. But what does it mean for these sections to be holomorphic? Well, we're going to define what it means to be holomorphic. We're going to define what it means by taking this operator. This operator we get for free from the complex, because X has a complex structure, so we get a splitting. So really, any connection you have will have a splitting. And we just choose the canonical connection for Hermitian metric, which is the Chern connection. And we define a bundle to be holomorphic. And what does it mean to define a bundle? It's enough to I just tell you what the sections are. And so I say, well, the sections of this holomorphic bundle are going to be smooth sections of this base complex bundle, but that satisfy this equation here. So these sections will define a vector bundle, and I call that, we define that to be a holomorphic vector bundle. And it's holomorphic in the sense that if I look at E, it's a complex vector bundle, right? Over a Riemann surface. Its total space is a smooth manifold, but its total space is not necessarily a complex manifold. But this holomorphic vector bundle, they're precisely the bundles whose total space is really a complex manifold. Yeah.
So the operator is telling you how to sort of take the complex structure from downstairs and sort of push it.
Yeah, exactly. Oh, that's okay. Thanks. Yeah, so that's actually a really good way to think about it. Is that when I endow this operator to make the bundle holomorphic, what I'm doing is I'm actually taking the total space, which is a smooth manifold, and giving it a complex structure, and then now it's a complex manifold. Yeah. Okay. Oh yeah, this one is better. Oh wow. Okay. Oh, that's cool. Okay. Like cleans the board for you too. Yeah, so now I'm going to add another object, which I'm just going to add a symplectic form. So let omega be a symplectic form, compatible with the complex structure on X. Complex structure on X. So it's a Kähler form. Kähler form. And because I'm on a Riemann surface, you know, all these objects exist. You can always find a symplectic form on a Riemann surface, so on. I'm going to define the volume. So let V, capital V, I'm just going to integrate over omega. So it's the symplectic volume, or I'm going to call it the volume of X. Again, this makes sense. This is a 2 form. I'm integrating over X, so this is fine. I want to define stability. So stability of these bundles, of these holomorphic vector bundles. So actually, I probably should introduce this after, but okay, that's fine. So stability of E, holomorphic vector bundle. So this is a definition. So a holomorphic vector bundle, vector bundle E over X. So this is of, I'm going to say, rank R, and degree D. Degree D is stable. So we call it stable if for every non-zero subbundle, which I'll call, I guess, F. Maybe not F. I'll do like a curly F subset of E. Satisfies this what we call the slope stability condition. So I have that F is going to be some non-zero subbundle, and it satisfies this inequality that the degree of F over the rank of F is strictly less than the degree of E over the rank. And this is typically what we call the slope of E. And this is, of course, which we call mu. So mu of E, we mean the degree over the rank. And this thing here is going to be the slope of F. So mu of F. Yeah, sure. So this is what we call, this is when what we call a holomorphic vector bundle be stable, is that for every non-zero subbundle, it will always satisfy this inequality, that the degree over the rank is always going to be less than the degree of E over the rank of E. If we allow for equality, so strictly less than is what we call stable. There's another notion, semi-stability, which is when you allow for equality. So if one allows for equality in the inequality, we call E semi-stable. Semi-stable.
Degree of a subbundle, that can change because you can have a subbundle with a first term class is additive. So
yeah.
Add the two together and it's different.
Yeah.
Like what kinds of examples are stable, or do you have an example of something that's not?
Yep. So, for instance, some of So example. I can think about, let's see. So on, let's say P1. So x equal to P1. So on x equal to P1, let E be O n plus O m. Actually, let's make it simple. Let's do O1 plus O. O1 plus O. So O is just a trivial bundle. Yeah, O is just a trivial bundle. So this is a non-trivial rank 2 bundle. So E has rank 2 and degree. It's just going to be the sum of the degrees of these things. So it's going to be C1 of E is equal to 1. So the slope of E is going to be the degree, which is 1 over 2, which is 1/2. So the slope is 1/2. Now, what I can do for subbundle, I can consider O1 as a subbundle. So consider O1. Well, this has, what does this have? This has as rank is 1, and it's just a line bundle, but its degree, degree is also 1. So for this bundle to be stable, it has to satisfy this, but it doesn't, right? This, so E is not stable as I have that the 1 is greater than 1/2. So this. Yeah. Yeah, exactly. Yeah, yeah. Yeah. So sums of bundles are never stable.
Any sum of any two bundles is not stable.
Yeah, the most you can get is semi-stability. You can find sum of bundles that are semi-stable, but they'll never be strictly stable. Never be strictly stable. So these are example. Well, I guess this is an example of a bundle that's not stable. An example of a bundle that is stable. Well, the examples that I know off the top of my head are complex. So,
rank 1 bundles.
yeah, exactly. So line bundles are always stable by definition because you can't find it. There's no non-zero subbundle of a line bundle. So line bundles are an example of a bundle that are always stable.
What about like tautological bundles over Grassmann? The Grassmann of like 10-dimensional complex planes.
Yeah.
C n plus k.
Yeah.
Tautological like anything bundle over that.
Yeah.
That kind of is stable.
What are its endomorphisms? So another thing. So I can say as a corollary maybe. So a bundle. Wait, I have to make sure this is correct. No, actually, this is not correct. This is only for specific case. So yeah, an interesting case that you can. Yeah, O minus 1 is the tautological. O minus 1 is tautological. Yeah, at the top of my head, I'm not sure. What I do know, so how I generate examples of stable bundles. So right now we're all over Riemann surfaces, right? But maybe this is just like a lemma for fun. This is not to do with Riemann surfaces. So this is lemma for fun. This is how I generate examples of stable bundles. So on x equal to P2. So this is a two-dimensional complex surface. So this is, two complex dimensions, 4 real dimensions. On x equal to P2, a holomorphic vector bundle E of rank 2. So it has to have specific rank 2 is stable if and only if H0 of end E is trivial. OP2. Sorry. Maybe, okay, actually, hang on a second. I want to do dimension of this thing is equal to 0. So as a complex vector space, it's just trivial.
So then that the group H up to 0, that's sections of this bundle.
Yeah. So the dimension of the sections of end E is going to be 0. So in other words, this is what people call simplicity. So this definition by itself, so a bundle is simple if and only if this holds, or a holomorphic vector bundle is simple if and only if this holds. And on P2, rank 2 bundle being simple is equivalent to being stable. So this is just like a fun little aside lemma here. but this is over P2. This is not true over Riemann surfaces. Yes. So as another quick definition of feeding back off of stability, so a holomorphic vector bundle curly E is polystable. So we're going to define polystable if E decomposes as a sum of subbundles. So it decomposes as a sum of subbundles EI, where the total ranks of the EIs equals the total rank of E, with each of the EI themselves stable. EI stable for all I. So we say that if we just have a holomorphic vector bundle, we say is polystable if it can be decomposed as a sum of stable bundles. Of course, polystable bundles are never stable, right? Because obviously it's a sum of stable things. So itself cannot be stable.
It's like a simple ring.
Yeah, similar. Yeah.
Sorry to
Yeah.
interrupt again.
Yeah.
So the fact that this vector space has dimension 0 and
Yeah.
there are no co-boundaries coming from a lower, does that just say that the only section of this bundle is the 0 section?
Yeah, it means that the only non-trivial maps, the only non-trivial endomorphisms you have are constant multiples of the identity. That's the only non-trivial, or I guess that those are the only endomorphisms you have is the trivial one. Yeah. So little h0, this is the dimension of big H0. So if you want, I could say that the dimension of H0, yeah, is equal to 0. Yeah. Okay, so now we can go to our first big theorem. So this was proved by Donaldson in, this was first stated in 1956, but then Donaldson kind of reproved it in a nicer way in 1982. So this is a theorem, and it's called the Narasimhan, so Narasimhan Seshadri correspondence. And this was proved in 56, but then also Donaldson. So this theorem they proved using very much like representation theory, fundamental groups, that sort of stuff, very topological. Donaldson proved this in 82 using more differential techniques. And I'm going to state how Donaldson did it rather than how Narasimhan Seshadri did it. But the result comes from Narasimhan Seshadri. So the theorem says that so again over Riemann surface, so let E be a holomorphic vector bundle over X with Kähler form omega. Then we get a result that states when E is going to be polystable. So E, as a holomorphic vector bundle, is polystable if and only if there exists a Hermitian metric H on E, so on the complex E, such that its curvature, which was f sub h, satisfies the following equation. So satisfies, what's the equation? Satisfies this. f sub h is going to be equal to minus 2 pi I times the slope of E over, so this is mu, the slope of E over the volume of X times omega tensored by the identity of E. So if you can find a Hermitian metric H such that its curvature, which was you take its associated Chern connection, you square that to get its curvature, if it satisfies this equation here, so if the curvature is going to be minus 2, so essentially this thing here is a constant. So this is a constant. It's a constant that depends on the volume of your space and on the slope of E as a holomorphic vector bundle. So this is a constant times omega tensored by the identity. So this is going to be a two-form. So this is a two-form tensored by the identity. So this is going to be some, it's an endomorphism. It's really the identity, but the entries are going to be given by omega and this constant. And if f is this is in a way saying f is equal to omega times the identity. Then your holomorphic vector bundle E is going to be polystable, so it'll satisfy. In particular, yes?
Just noticing like the left-hand side and the right-hand side both have things that relate to the first Chern class.
Yeah, I think the 2 pi I it comes from like writing out the definition of Chern class and when you get that constant 2 pi I or something. Yeah. Exactly. Yeah. Yeah, exactly. Where was it? Yeah, I had it. I erased it. But yeah, it was like 1 over, or I think it was like I over 2 pi of some integral or whatever. Blah blah blah. Yeah. And of course v, since we have the volume here, that's why we want x to be compact so that we can actually get some finite thing here. The important thing is that when the slope is 0, so when mu of e is 0, what this corresponds to is the degree of e being 0. So this is kind of like a corollary or like a remark. And this is really the correct statement of I guess Narasim and Seshadri is that if E has degree 0, so degree 0, then the equation becomes fh is just equal to 0. So what this, which corresponds to nabla sub h being flat. So nabla sub h being a flat connection. So what this means is that there's actually a one-to-one correspondence between polystable bundles with degree 0 and flat connections. And that's seen by taking u of e to be 0. This is also kind of like related to Hermitian-Einstein metrics and Hermitian-Einstein equations. This is kind of like a special case of that. So, yeah. And then so there's a corollary of this. So this is what so this theorem tells you, okay, when is E polystable? It's polystable if and only if you can find a metric, a Hermitian metric that satisfies this equation. And furthermore, E is stable, so actually just upfront stable, if nabla sub h is an irreducible connection, so is irreducible. And what do I mean by this? So irreducibility means that for any, so I'm going to call it, I don't know, let's call it a section of the endomorphism bundle of E, we have that nabla sub h of A is 0. So this is the induced connection on the endomorphism bundle. So this thing is going to be irreducible if and only if for all A sections in the endomorphism bundle, we have that the induced action of nabla H on the endomorphism bundle of the section is going to be 0. If we have that nabla sub H is irreducible, then E is actually going to be stable as a bundle itself. So all this is proved in Donaldson's paper from 1982. The key takeaway from this, the main, yes. Yeah, no, you're good.
So in the case where we're back, where like X is a Riemann surface.
Yeah.
Complex.
Yeah, exactly. Here X is a Riemann surface in the theorem. Yeah.
So it is. So if you have a bundle over a Riemann surface with first term class 0, doesn't that make it a trivial bundle?
Yes. Yes.
So like over here, your bundle, all of these are trivial bundles with flat connection.
Yes.
Does that mean that if you have a non-trivial bundle, you can't have a flat connection?
No, that's not true. You can still have I'm going to see if I'm making this up. You can still have a rank R vector bundle over a Riemann surface that has a flat connection, but is not trivial. So like O minus 1, right? Any line bundle will have curvature equal to 0, right? Because it's just rank 1.
Yeah, I'm just like trying to reconcile with like what the statement is saying. Maybe I'm just like not. It's not enough no. Like this.
Yeah.
The whole point is what curvature 0.
Well, yeah, because so you're right. Any trivial bundle will be flat because it's just trivial. So it'll have, you can find a flat connection on it. But say any line bundle, any line bundle, so rank 1 object, will also emit some flat connection because the curvature will be 0 because it has to be. So I can think of O minus 1, which is non-trivial, but it'll emit a flat. Yeah. But it should be noted, yeah. So I'm implicitly thinking that that X in this theorem is a Riemann surface, but actually you have an analogous statement where X is any complex manifold. This theorem is still true for X any complex manifold. Compact complex manifold, I should say. The main point that I wanted to take away, and this is the key takeaway, is that I have that solutions to PDEs corresponds to stable algebraic objects. And when I mean solutions of PDEs, I mean the solutions are going to be metrics. And this is kind of the theme of what motivated motivated Hitchin to study Higgs bundles and generalizations of this. But this is also a very algebraic way of studying gauge theory, right? Gauge theory, people are interested in solutions of PDEs, and algebraic geometers will say, well, okay, what if instead we found a correspondence between solution of PDEs with some sort of algebraic objects that we can study, like holomorphic vector bundles, for instance. And then you could study the moduli space of these objects to give you information about what's happening over here. So this was all very classical. I didn't talk about Higgs bundles at all or anything, but now we're in a position where we can introduce Higgs bundles. So what I'm going to do now is I'm going to essentially try to do another theorem, a generalization of this. I'm going to generalize that theorem. This is what Hitchin did in late 80s or so. Yeah.
So we said that we want X to be compact, we want V to find a number.
Yeah.
And has anyone thought of dealing with non-compact surfaces and having V be infinite, but having some notion of taking the limit of mu of S, mu of E over V to be actually a finite thing and
well, you mainly want compactness because you want to take an integral. Integrals don't really make sense on non-compact objects. If your thing was non-compact, then you would have to somehow restrict yourself to like compact submanifolds and then integrate over there. You can still study Higgs bundles over non-compact things. You can. Why not? It's just that you won't get a nice kind of correspondence like this. Yeah. But because we want to integrate, we want our space to be compact. Yeah. So where am I? Okay, yeah. So now I'm going to move on to Higgs bundles. So now, so as before, let H be a Hermitian metric. On X. On X, which is again X is a Riemann surface with genus greater equal to 2, compact Riemann surface. On X, and the Chern connection nabla H decomposes into these two operators, partial E plus partial bar E, and we know that its curvature F sub H is going to be a section of a global section of the endomorphism bundle tensored by omega 1, 1. So it's omega, it's matrix of 1, 1 forms. So now we're going to introduce a section. So introduce a section which I call capital phi, which is going to be a map from E into E tensor T star 1, 0, X. So introduce a section which is a holomorphic map. So a holomorphic section, holomorphic bundle map. So it takes in sections of E and sends it to sections of E tensored with the 1, 0 part of the cotangent bundle of X. So this is going to be like dz. Tensor things by dz. This is called so phi is called a Higgs field. So a Higgs field for E. So it's holomorphic, right? So so it's holomorphic. So as phi is holomorphic, I have this equation that partial bar E phi is 0. And this is kind of an abusive notation, but partial bar E acts on sections of E, but phi is not a section of E. It's a section of phi is a section of H0 X and E tensored T star 1, 0 X. So it's a section of the endomorphism bundle of E tensored by T star 1, 0 X. So this is just the induced action of partial bar E onto this bundle. So phi is holomorphic, so we have this equation. This is just by definition. I want to do some, locally, what does phi look like? So locally, phi looks like, so I'm going to write little phi dz. So phi I, dz I, actually it's just dz, there's only one variable. So phi dz for phi in R by R matrix, of holomorphic functions. So, or in other words, you can think about it being a matrix of holomorphic 1 forms. Is also how you can think about it. R by R because E is I didn't say it, but E is rank R. E rank R. Holomorphic vector bundle over X. So I need to describe a few things you can do with phi. So because I have my Hermitian metric, I can define some adjoint operator or an adjoint operator that takes in phi and sends it to its adjoint. So with H, we can define the adjoint Higgs field which I call capital phi star h, as a section of, so it's still going to be a section of end E, but instead of tensoring by t star 1, 0, it's going to be tensored by t star 0, 1, x, as follows. So locally, define, how am I going to define this? Define phi star h as, again, little phi star h dz bar, where, what is this little phi star h? Phi star h is defined by h of phi u comma v is going to be the same as h of u phi star h v. So it's just the adjoint of little phi here. Little phi here is a matrix, so I'm applying this matrix. U and v are sections, so u v sections of E. So I can think of phi as being some endomorphism, takes in some sections, sends it to a section, and I'm saying that this is going to be equal to this. This is the adjoint. So I guess this is how I'm defining this adjoint thing here. And why do I need this? Because I'm going to state this theorem of Hitchin. So, yeah.
I didn't quite understand for the use notation remark how del bar acts on that. You mentioned it, but could you possibly write it down how it acts on define del bar?
Yeah, how it actually acts. Again, this is just my memory being awful. So this del bar E is a connection, right? And given a connection on a bundle, I get an induced connection on its like tensors and on its wedge products and so on. So this thing here, del bar E on end E tensor t star 1 comma 0 x acts as, so I'm going to have the induced connection on end E, acts as partial E bar tensor partial E bar dual, right? Given a connection, you get a canonical connection on its endomorphism bundle by, you can define a connection on a dual bundle. Given that end E is E tensor E star, I get this thing, and this thing acts as a connection on end E tensor E star. And it's going to act on here, on this part. How's it going to act on this part? Let's see here. Let me think. Actually, I think it's just the identity. Just identity t star, comma 0 x. No, something like that. Yeah. I'll have to. I have to go back and think more about how to exactly do it. But yeah, this is how this part acts on the endomorphism part here, just like that. Yeah, that's for physics reasons that I don't understand. Yeah. I mean, in gauge theory, you have a lot of things called Higgs fields, and typically they're, I don't know, some section of some bundle. So yeah. This is something Hitchin called this Higgs field. So yeah. You can blame Hitchin. Yeah. But I think its roots go back to like Atiyah, Donaldson, these types of people. Yeah.
Sorry, I think this is a very big elementary question, but phi is that map there, and why is that also true, the statement above it?
Oh, that's just by definition, right? So when I mean H0x here, I mean it's a global section of this bundle.
Right.
As it's a global section of this bundle, right? ND I can write as E tensor E star. And so on each fiber, sections of E tensor E star are just linear maps from E to E. And so it's a map from ND tensor this thing. So on each fiber, it's going to be a map from E to E tensor this thing. Yeah. Where am I? Yeah. Okay. So, okay. Oh, I'm erasing what I already wrote. Whatever, it's fine. Yeah, exactly. Yeah. You just do conjugate transpose and you're fine. So, just as there's a notion for stability of, well, I guess I should introduce. So the pair E, comma phi is called a Higgs bundle. Higgs bundle. So it's a tuple where E is a holomorphic vector bundle on X on your Riemann surface, and phi is a holomorphic section of ND tensored with the 1,0 part of the cotangent bundle of X. So just as we defined stability and polystability, stability for holomorphic vector bundles, we can do the same for Higgs bundles. We can do the same for Higgs bundles. And the definition is actually identical. We just have to impose that the subbundles that we're checking stability on satisfy certain conditions. So definition, a Higgs bundle E comma phi is stable if, so not just every subbundle, but if every phi invariant subbundle, I'll state what that means, subbundle F E. So what does phi invariant mean? Phi invariant means so phi of F is a subset of F tensored T star 10X. So we call a subbundle phi invariant if phi applied to F sits inside F tensor T star 10X. So we call the pair stable for every phi invariant subbundle F. We have, and it's the exact same inequality, that the degree of F over the rank of F is strictly less than the degree of E over the rank of E. So we have this slope condition satisfied. So note that for stability, being stable as a vector bundle is more, what's what I'm looking for? This is more, being stable as a vector bundle is more restrictive. Being stable as a Higgs bundle is that we're looking for stability of E, but we're only checking the subbundles that satisfy this inequality that are phi invariant. If it's not phi invariant, we don't care. So you can have a vector bundle E be not stable, but with a given phi, it be stable. Yes.
If like phi is basically like the identity of the part, and maybe something else, does that recover the old definition? Like, is there sort of a trivial?
So it's not that phi is the identity on E. It's going to be any endomorphism of E tensored by it.
What if like you choose like the most trivial possible?
I could choose phi to be 0.
Does this recover stability?
When phi is 0, then it's just stability of vector bundles.
Okay, because phi invariant,
everything's phi invariant when it's 0, right? So yeah. So that's a good thing to note, is that when phi is equal to 0, you just recover stability of vector bundles, of holomorphic vector bundles. So when phi is equal to 0, this definition recovers stability of E as a vector bundle. I have an example of, actually, I don't know why I'm going over here. It's over here. Okay. here is an example. So, okay, I'll do an example now. So what's an example of a stable Higgs bundle? So so this is where I can tell William's going to have questions that I won't be able to answer. So consider the holomorphic vector bundle, and it's going to be, E is going to be, so K, well, I'm going to write K now as, so K sub X to the 1/2 plus K sub X to the minus 1/2, where, so K sub X is the canonical bundle, which is just going to be, T star 10X, which is what we've been writing so far. And K to the X to the 1/2 is a choice of square root of K. Of square root of K. And it should be noted that this choice is not unique. There's actually 2 to the 2g. There's 2 to the 2g choices of square root of K. Yeah, square root of K. Yeah, so how are these things defined? So, I mean, I define it as it's a choice of the square root of K, but more precisely, K X to the 1/2 is a line bundle. So it's a line bundle on X such that if I take its square, so if I tensor it twice, I get K, such that K sub X to the 1/2 tensor K sub X to the 1/2. This is isomorphic to K. I get my canonical bundle back. Yeah. And how many different decompositions do I have of this? Well, for a Riemann surface of genus G, there's exactly 2 to the 2G choices of different decompositions I could choose. So this is just one of them. So this is a rank 2 bundle, and its degree is 0. Because the degree of this is 1/2, the degree of this is minus 1/2, the degree sum. So this is an example of a degree 0 rank 2 holomorphic vector bundle on your Riemann surface. So I'll write that down over here. So E equal K sub X 1/2 plus K sub X to the minus 1/2 is an example of a non-trivial example of a rank 2 degree 0 holomorphic vector bundle on X. So I'm going to use this to construct a Higgs field. So I'm going to define phi. This is a map from E to E tensored Kx, right? Kx, remember, is just the 1,0 part of the cotangent bundle of X, as the 2x2 matrix. So phi is going to be 0, alpha, 1, 0, where 1 is the identity of K sub X to the 1/2 is the identity, and alpha is going to be a what we call a quadratic differential. And alpha is going to be a global section of K sub X, tensor K sub X. So alpha locally looks like F dz tensor dz for some holomorphic function. F. So, okay, to recap, so I have this bundle here, which is going to be k sub x to the 1/2 plus k sub x to the minus 1/2. And to choose a Higgs field, because this bundle is split globally, my Higgs field is just going to be a 2 by 2 matrix. It's going to be a 2 by 2 matrix globally, where it's going to be 0 on the diagonal, and on the off diagonal, the bottom here's 1 is going to be the identity on k sub x to the 1/2. And alpha here is going to be a section of k sub x tensor k sub x. So it's going to look like some holomorphic function times dz tensor dz. So we call this a quadratic differential. I'm not taking a wedge product here. I'm taking a tensor product. So this thing is non-zero. Right? So this defines a stable Higgs bundle. And I'll prove that. So note stable. Remember, because this thing's a sum of line bundles, this thing will never be stable, right? But by introducing this Higgs field, the pair E phi is stable. So it is going to be stable as the Higgs bundle. How do we show that? Well, what do we need to check? We need to find all phi invariant subbundles. We only need to worry about the phi invariant subbundles. If there's a subbundle that's not phi invariant, we don't care about this inequality. We only care about this inequality on the phi invariant subbundle. So what are the phi invariant subbundles of this thing here? Well, we can check that. So first of all, k sub x to the 1/2 is not phi invariant. Why is that true? Because, well, if k to the 1/2 was phi invariant, then we would have that is not phi invariant. If it was, we'd have that phi of kx to the 1/2 would be a subset of kx to the 1/2 tensored with k. But k sub x to the 1/2 tensored with k, this is isomorphic to k sub x tensored to the 3/2. So this is just k sub x to the 1/2 tensored 3 times. But, okay, what happens? So what are all the entries? So how you should imagine this matrix, I always like to imagine it as it acts on some vector where some element here, uv, where u is going to be some element in k sub x to the 1/2, and v is going to be some element in k sub x to the minus 1/2. So maybe it's better to write it like k sub x to the 1/2, k sub x to the minus 1/2. So, I mean, 0 takes in something here and sends it to 0. That's fine. Alpha, what does alpha do? Alpha, if you do matrix multiplication, alpha takes in something in k to the minus 1/2. So alpha takes in something from k to the minus 1/2. And where does it send it? Well, it takes in something here and it sends it to something up here. If you do the matrix multiplication, right? So this times that plus that times that gives you something here. So it gives you something on top, which is something in here. So this maps to k sub x to the 1/2 tensored by k sub x. Yeah. So, no, this isn't. No. I'm not saying it's a section of an endomorphism bundle. So this is k. One sec. Let me write this down and then okay, maybe let me explain this better. How we figure out how these entries act, right? Is you imagine that what does this matrix do? It will act on some vector where the top component is going to be something in kx to the 1/2, and the bottom component is going to be something of k to the minus 1/2, right? So really, how do these things work? Alpha, if we just look at alpha as a section, it takes in something in k to the minus 1/2, right? Just by, if we actually think about this literally as being matrix multiplication, it takes in something here and it sends it to something up here.
phi has to spit out something in E, but also something in KX.
Yeah, so that's why I'm also tensoring by KX here because phi is itself a map from E to E tensor KX. So whatever the matrix part does, I have to make sure I tensor by this thing as well at the end. So that's why I get this. That's why I get this.
And then for the one.
So the one, what does the one do? The one takes in something from k to the 1/2. This is k to the 1/2, and sends it to something down here, which is k to the minus 1/2. K to the minus 1/2 tensored with k. But this is isomorphic to k to the 1/2. So this will be the identity. And alpha, so this thing's a quadratic differential, but viewed as a bundle map, will be something that takes in k to the minus 1/2 and gives it to something here. Yes, 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 yes.
So, looking at the alpha
Yeah.
up there, and comparing the alpha down,
Yeah.
down there, the first KX is going to be you're going to add the power of the minus half and the
Yep.
and the one. That's where you get the
3 halves.
That's where you get the first 1/2, and the second tensor, like tensor KX, is just you plug in the KX there. So you're doing nothing to that.
It's more like this thing is a quadratic thing. So it's some section, it's some dz tensor dz. What this thing will do, it'll take in a k to the minus 1/2.
Yeah.
So you can think about it as k, right? If I take kx to the 4, squared, this is isomorphic to, this is just equal to k sub x tensor k sub x. Now, this is the same as this is the same as 1/2. This is the same as k to the 1/2 tensor k to the 1/2 tensor k to the 1/2 tensor k to the 1/2. This alpha, well, if I take in something here, this something in minus the 1/2 will cancel with one of these things here, leaving me a something of here, which is k to the 3/2. Yeah. I can feed it another 1/2, and then it'll give me something in k to the 1/2, which is going to be something in k. Yeah. So if you look at these bundles, or these sub-bundles, so k to the 1/2 gets sent to this, but for k to the 1/2 to be phi invariant, you would need that. So okay, let me write actually this all down over here. I actually kind of already wrote out what the k to the 1/2 being phi invariant is. So for k to the 1/2 to be phi invariant, phi would have to send this thing to this. But let's look at all the elements. So the only thing that sends k to the 1/2 to something is the identity, right? The identity sends k to the 1/2 to k to the 1/2, which is not k to the 3/2. So k sub x to the 1/2 is not phi invariant. It's not phi invariant. Now, if you look at k to the minus 1/2, for k sub x to the minus 1/2 to be phi invariant, what would we need? We would need phi to send k sub x to the minus 1/2 into k sub x to the minus 1/2 tensor k sub x, which is isomorphic to k sub x to the 1/2, right? But what is phi? Where does phi send k to the minus 1/2? Well, it's alpha here, and alpha sends k to the minus 1/2 into k to the 3/2, which is not this. So k sub x to the minus 1/2 is not phi invariant. So actually, none of the sub-bundles the obvious ones anyways, are fine variant. There's actually a result that says that, so k to the, it's, I'm not going to prove this, but it suffices to actually just check fine variance on this thing. If you have a subbundle that's maximally destabilizing, so it's the destabilizing bundle of maximum degree, then it only suffices to check the fine variance on that thing. But in any case, none of the components are fine variant, so we actually don't need to check this on anything. Yeah. So yeah. So that's, yeah. I want to sweep that under the rug. Yeah. It's actually so that's why this alone right here is enough to prove that it's stable, because k sub x to the 1/2 is the maximal destabilizing subbundle. So k sub x to the 1/2, right? It's rank 1. Its degree is 1/2. So it's going to be 1/2, and the degree of E. Hang on a second, actually. Degree of E here is 1/2. Yeah. So k sub x is so this bundle alone is actually semi-stable. It's going to be semi-stable because it's rank 2, degree 1. So its slope is 1/2. And the slope of this thing as a subbundle is also 1/2. Because the degree is 1/2 and the rank is 1.
Why is it equal to 1/2? X is just some Riemann surface, right? Shouldn't X have its own, this T star 1, 0, X should have its own degree that's not just 1, right? Like it's a number.
Yeah, exactly. But this is not k sub x. This is k sub x to the 1/2.
Yeah, so it should just be half of the degree of k of x, because it's the square.
Yes. Yeah, I think that's correct. So k sub x here.
If we define degree.
No, you're right. You're correct. Yeah. So it's So it's going to be 1/2 the degree of this thing, but this is what's the degree of k sub x? I feel like that is just 1.
I forget, how does the T star x relate to like those usual tangent bundles?
Like so I mean, this thing comes from the decomposition, right? So like T star x decomposes as T star 1, 0 x plus T star 0, 1 x.
Yeah. Aren't those two like as complex bundles with one another?
Yeah, they're complex conjugate to each other.
Okay. Yeah. So then like the even number coming from the first term class of the tangent bundle at x, that already gets divided into 2 to get to the kx.
Mm-hmm.
I see. So work. How do you know there's the square?
Oh yeah. Like how there's like 2 to the 2g choices of this thing.
Or how do you even know there is one? Because it's possible that like x could have Euler characteristic like 2, or rather, or 6, say, so that the genus is big enough, and then the first Chern number for x is going to be 6, and so the first Chern number for this bundle T star 1, 0 is going to be 3. And so to go from kx to kx to the 1/2, like you would need to have first Chern number 3 over 2. But the Chern numbers are always integrals. So
Yeah.
So this was like the alarm bell. Like you can't have the degree equal to 1/2. So I was confused where that came from.
Degree can't equal 1/2. Yeah.
We should figure this out.
Yeah, there's definitely There's definitely something I'm missing that I don't know why. So this thing here, I actually don't know how to prove this. I know this is true. I don't know why it's true.
Yeah,
this
like
statement here.
Genus, like you have your Chern class that's classifying your bundle, and you
Yeah.
like change the sign twice.
Yeah.
Component, so I think that's why you get that number.
Yeah.
But in order to get a square root, I still do like your kx.
Yeah.
As a Chern number.
Yeah, maybe that's true. So I mean, well, what I wrote down here is correct. This is real, right? There's something that I'm missing that maybe that will clear up. Like maybe you can't have, maybe it needs to be some specific condition on Chern classes or something that I'm not thinking of right now. Anyways, so yeah, kind of sweeping stuff under the rug. This is an example of a stable Higgs bundle. So E phi is a stable Higgs bundle. Okay. Now I want to go into this theorem, which is kind of a generalization of the theorem that was over here. The theorem before was only relating polystable and stable. I guess I should real quick do define polystable. So polystable is defined in the exact same way. So a Higgs bundle E phi is polystable. Similarly, if now instead of E decomposing, E decomposes and phi decomposes. So if E comma phi decomposes as a sum of, say, E sub I, phi sub I, with each E sub I, phi sub I stable. So you can think of it as the bundle decomposing, and the bundle decomposes with phi decomposing, and each pair in the decomposition defines itself as a stable Higgs bundle. So this theorem, which is from Hitchin, I can't remember exactly, 86, 87. It's definitely somewhere here. So a Higgs bundle E phi over a compact Riemann surface X is polystable, so satisfies this definition here if and only if there exists a Hermitian metric. So again, if there exists a Hermitian metric H on E satisfying the equations, and this is what, okay, the equations are satisfied is going to be, so again, F sub H. So F sub H is the curvature of the Chern connection of H, plus this commutator phi, comma, phi star H. So this is the adjoint of phi with respect to H is equal to minus 2 pi I, is set the same constant, so minus 2 pi I times the slope of E divided by the volume of X times omega, tensored with the identity of E. Omega was that symplectic form. I guess I should write X with Kähler form omega. So we have that this is satisfied, and we have that this equation partial E bar phi is equal to 0. This we already know that this is true just from the fact that phi itself is a holomorphic section. But this is the big main equation here. This is what people call Hitchin's equations. So again, we have that Higgs bundle, E phi, is polystable if and only if we can find a metric H such that its curvature satisfies this big equation here. This commutator is the same as in coordinates. We know that phi is going to be a matrix of one forms. This is a matrix of one forms. What we do is we take the matrix part, do the commutation, and then wedge the form parts together. So that's what this means. Yeah, so I did over. Yeah, I did. So phi. Yeah. Yeah, exactly. Yeah, that's exactly it. Yeah. So you take, so like phi star H is equal to phi So I should say if phi is equal to phi dz, then phi star h is equal to phi h star dz bar, where, yeah, phi star h is equal to phi, the conjugate transpose. Where this is viewed locally, this thing's just going to be an R by R matrix, and so you just do this on the matrix part. And so this commutator, what this means is I take, again, these are matrices, so I take the commutation of the matrices and I wedge these two together. So phi comma phi star h is just the regular matrix commutation of phi and phi star h, the regular commutator, times dz wedge dz bar. So this thing is a 1-1 form. This thing is a 1-1 form. This equation makes sense, and omega here is also a 1-1 form. Well, I mean, symplectic form. I really do mean Kähler. It is Kähler form. It's a symplectic form that's compatible with the complex structure of X. It's just a Kähler form. And it's yeah. So these are the Hitchin equations. So this is what it means for the pair to be polystable. So the pair is polystable if and only if these equations are satisfied. The pair E comma phi is stable, so just outright stable, if and only if we have that there exists an H, and so there exists an H that satisfies the equations, satisfies the Hitchin equations, and the connection. So now instead of asking for in the other theorem, it was the Chern connection of H was irreducible. In this case, it's going to be the connection, which we call, I guess, capital D, or I call capital D, which is going to be the Chern connection plus phi star H is irreducible. So this Chern connection is a connection. Turns out if you add phi and add phi star, this also defines a connection. So this defines a connection. And this is what people call the Hitchin connection. And you can do a calculation. It's not so bad. If you do a calculation, d squared, if you compute d squared, so the curvature of this connection, you actually get the curvature of H plus the commutator of phi and phi star H. So d squared is actually just this part here. So I could have written the equations in terms of d squared if I wanted to. And so you have an analogous thing where if the slope of E is 0, so the degree is 0, then I get this is equal to 0. That's equivalent to this connection being flat. But this is yeah. So it's not the Chern connection. It's a specific connection where you add phi and phi star H. Of course, when phi is 0, you just recover the Chern connection. And of course, when you set phi equal to 0, you recover exactly Donaldson's previous result. So this is kind of the magic of these Higgs bundles. So, how long have I been going for, by the way?
1 hour 34 minutes.
Okay. I'll state one more fact, and then I'll end it for today. So now, we know that these Higgs bundles, I guess polystable Higgs bundles, correspond to solutions of these Hitchin's equations. I can define what it means for two Higgs bundles. So if I have two separate Higgs bundles, I'm going to define an equivalence relation between the two. So suppose E phi and F psi are two Higgs bundles over X. I'm going to define an equivalence relation between the two. So we say E comma phi is equivalent to F comma psi if there exists a holomorphic bundle map, I'll call it G from E to F. So this is a holomorphic bundle map such that I can write phi as G inverse composed with psi composed with G. So really, it's a conjugation result. I call E phi and F psi, they're going to be equivalent to each other. If there exists a holomorphic bundle map such that if I take G inverse psi G, I recover phi. Now, this is technically a type abusive notation. G is a map from E to F. Psi takes in a section of F and sends it to a section of F tensored K. So really, this should be G inverse tensored the identity on K. But it's, whatever. Yeah. So this, that's fine. But I'm just going to leave it. People usually just write it like this. So now I can define the moduli space, but I mean in a very informal way. I guess again, this is work that Hitchin did again in Hitchin has a paper, self-duality equations on the Riemann surface, or on a Riemann surface. And this is where he does essentially goes through everything I just talked about, but he does more about like the topology and whatnot of the moduli space and showing it smooth, and does a lot of symplectic geometry on the moduli space and whatnot. But I can define curly M Higgs. So as a set, it's going to be the set of all E phi such that E phi is stable. So I'm only going to be looking at stable pairs. Mod out by equivalence. Hitchin proved that M Higgs is a, what did he prove? It's a non-compact, so the space is non-compact, but it's a hyperkähler manifold. Hyperkähler manifold of complex dimension 2r squared plus, or 2r squared times G minus 1 plus 2, where G is the genus of X and R is the rank of your bundles here. So yeah, E phi where rank of E is equal to R. So for some fixed R.
That's sort of one for each possible rank.
Yeah, the moduli space is actually going to be parameterized on the rank and the degree. But so for every choice of R and D, you get a different space. But it turns out the dimension doesn't depend on the degree. It only depends on the rank. Yeah. So it's non-compact. You can compactify it, but that's intense. And it's hyperkähler in the sense that you have 3 complex structures. And you can think of each of the complex structures coming from these equations. So let's see if I get this right. So this equation here gives you one complex structure. This equation decouples into a real part and an imaginary part. The real part gives you one complex structure. The other one gives you another. So that's 3 complex structures. In other words, you get 3 moment maps from these equations. And yeah.
You know what a moment map is. I don't. So told you. They still don't know. So it's not a good word.
Yeah, that's fair.
I'm doing the physicist for the day, but like steps.
Additions.
That's why I have like.
Yeah, that's all I have for now. Actually, I'm just gonna end it here. I'll do a part 2 some other time.
Nice.
Yeah. Yeah, so I didn't even get to any Vafa-Witten stuff at all. Just the hitch and stuff. Yeah,
That's why part two.
it's true.
Questions. If anyone has questions. If not, I'll go first. Questions. So okay. For have you seen any of this last part done categorically?
Yes.
Yeah. Okay.
Because my friend, one of my good friends. So remember that the one student I said that we're doing this like higher category stable whatever nonsense. He's applying that.
Nice.
Don't ask me how or what. I have.
I see, but to these
Yeah.
moduli
In a way, it's like like instead of looking at moduli space of these Higgs bundles, he's like looking at families of Higgs bundles, and over this family, describing some sort of category nonsense.
And do people take hyperkähler quotients since now it's a hyperkähler manifold? I don't like.
Yeah, so I mean, yeah, like implicit in this construction, it's like hyperkähler quotient. It's like you have again 3 moment maps, and you're taking like 3 different symplectic quotients. But yeah, that's how it's constructed.
Okay. And is that like implicit in the modding out by that equivalence relation?
Yeah.
Oh, okay.
Yeah.
Thanks.
Did he use the word hyperkähler? Like, I don't know how old that word is.
Yeah, that's a good question. In his paper, it does. So I'm guessing. So hyperkähler, it definitely goes back to late 70s.
Okay.
Yeah, it's interesting because I mean this work that did 67 for Higgs bundle, he actually has a previous because okay, what's something that I didn't talk about that I probably should have is that his Hessian equation, how you actually derive is you start with the self-dual Yang-Mills equations over R4. So self-dual
Dimensionals.
Yeah. So you start with like it's like on R4. You look at you have some connection on R4. Then you look at the equation star f is equal to minus f. So in this case, anti-self-dual. So anti-self-dual. So I'm looking at connections whose curvature satisfies this equation. And then what you can do is this connection is going to be on R4. It's going to be a function of 4 variables, x, y, x. What you can do is you can call dimensional reduction, dimensional reduce. You assume that the connection is invariant under 2 of the variables. Say like x3 and x4.
Like translation.
So it's you're imposing a translation variance, 2 of the directions. By doing so, then actually writing out this equation, you get different equations. Actually, in fact, you get these equations where this phi is going to be written in terms of the invariant coordinate directions. But like so again, you look at anti-self-dual equations on R4. You do some dimensional reduction, which corresponds to imposing translational invariance on the connections. And these equations on R4 transform into equations on a Riemann surface. So one-dimensional complex curve, or 2 dimensions. So half this dimension. They correspond to this. And but this thing is not used. So people have been doing this for a while. Like there's a bunch of different pseudo equations coming from this. So if you impose translational variance in one direction, then you get like which is like for magnetic molecules. Okay. If you impose like 3 translational variants, then you get something like Nahm's equation. So you get a bunch of known families of equations by doing the dimensional reduction trick. And Hitchin just in 87 was like, what happened? Like imposing 2. And then like, oh, moduli space is hyperkähler.
What if you do rotational invariance?
Alexandra's K3, of course, don't think we ever saw that. We saw like noms and Bogonomi and Hitchin, but
Doesn't mean it doesn't exist. Probably, I don't know.
It's like someone must have.
Yeah,
There's just like
someone's thought of it.
probably.
every symmetry they could possibly come up with, they probably tried to come up with
Oh,
a new
yeah.
equation.
Probably.
Yeah, so this is actually how Hitchin originally constructed like his paper that he's using this stuff. Starts with this, and then derives these equations. And says, oh, these equations correspond to these pairs, and these pairs are stable. And
So we got these equations.
Yeah.
Are they any good?
Yeah.
Yeah, sure.
And then he said, oh, if I look at the moduli space of these pairs, which correspond to solutions of these, then the moduli space is hyperkähler of this dimension. It's like a 100-page paper.
What was the abusive notation you mentioned here for this phi being this?
Yeah, technically this should be written actually as G inverse composed with the identity on X of X.
Okay.
Should be the identity.
That makes sense. Yeah. Nice.
Because psi takes in
So it takes an f and spits out f tensor x and kx.
yeah, which is why I have
Nice.
that's
Awesome.
yes.
Right.
And there's another completely, I'll probably talk this next time, but this method, so this is just like a cool little fun fact that Higgs bundles arise as solutions. When someone actually wants to construct a Higgs bundle, like an actual pair, we don't touch these equations. These equations are too hard, right? P is too hard. So there's an algebraic way of constructing them, which is something called a spectral surface, or a spectral cover, I should say. To every Higgs bundle, U5, there exists a manifold, which we call spectral cover, which essentially parameterizes the eigenvalue or the eigenvector. So the Higgs field, right, locally is a matrix, and so this matrix has a characteristic polynomial. So I can define a characteristic polynomial, and the zero set of this characteristic polynomial is actually this. And so people usually study the characteristic polynomial Higgs field, and with that you can construct. That's how I do my own.
So these are like finite matrices. So they only have like discrete.
Yep.
So it's sort of like locally you have like these parallel moving eigenvalues that might
Yeah, so
meet somewhere, or
yeah. So that's the branch. So actually, I'll do more about this next time. But yeah, so for every what you can do is for E5 on X can construct a double cover, or okay, an R to 1 cover. I guess X. How do people call it? Sigma, I guess people call it sigma. To X, so this is R to 1, where sigma as a set, right, is the zero set of characteristic polynomial phi. So I'm not going to go into detail about this, but essentially you look at all the zeros of this thing, and this gives you the space. The space is going to be smooth, and you actually get an R to 1 cover.
what were you saying? It's a branched cover.
So
Like
it's a
you
branch.
can-
It's a branch cover. It's
Like
precise.
there's going to be places where your matrices suddenly have like double roots.
Yeah, exactly. It's exactly where the eigenvalues of phi are. Yeah. So this is where this thing's going to be branched. And so it's a lot easy studying, and also because this thing is actually going to be a Riemann surface. And what you can do is you can study line bundles on this thing. And if I push forward the line bundles to here, because this is R to 1, the line bundle becomes a rank R bundle, and I'm essentially constructing all bundles here possible. Whoa. So So this is something that, again, Hitchin did this, of course. It's called the spectral correspondence.
Is that the same paper, or is it?
It's a part 2.
Okay.
Yeah.
Wow.
So this paper is called self-duality equations on Riemann surface. That's I think 86, and then 87, he does this stuff in a paper called integral systems and stable bundles. Yeah. So this is where the integral system stuff comes into